Now, we were in the middle of a nasty proof. We discovered the mass is 1 over 16 pi times the integral over a space-like surface of HAB del A epsilon dagger del B epsilon minus 1/4 of epsilon dagger HCD HAB R D B E F C A gamma E F epsilon, and 3 other terms which were oops. So that, I think, is where we had got to. The first term is positive, as requested. The second term is complicated, but we had managed to find a nice expression in terms of the energy-momentum tensor. And that boils down to the following expression. After use of this identity, which we derived, this becomes, that's right. So the term involving the curvature two A's, absolutely right. A, B. Rough guess, the last A should be a C. I would think that's probably right. And the term involving the curvature after the use of our identity is 8 pi times T D T dF, the energy momentum tensor, epsilon dagger gamma F gamma C epsilon times T C. Now we want to think about this term a little bit. This is the energy momentum tensor of matter. This is a time-like vector which is normal to the surface sigma. So what this does is to essentially, if you think about some orthonormal frame, make this a 0 and that makes that a 0, which means that this thing is going to be a time-like vector. That's because gamma 0 times gamma 0 is 1. So this collection of stuff is time-like. This is a time-like vector, not necessarily the same as this one. So we're talking about T0 something being picked out in this expression. Now if you think about T0 anything, it's going to be the momentum flux vector. And that had better be a time-like vector. So provided the energy density of whatever matter is doing is acting as the source is positive, then this term must also be positive. Now let's go back to this formula. So this term has nice positivity properties, this term has nice positivity properties, I'll summarize all of that in a little bit, but we're still left with these three terms here which look like they're awful. In actual fact, these three terms cancel. They give you 0 identically. And all you need to do is to use the definition of the covariant derivative of the time-like normal to do that.
We try to come up with the definition. I mean, the whole purpose of this argument is to come up with a definition of mass, which has positivity properties, right? Mm-hmm. So how can why are we allowed to always say that all matter has a positive momentum flux?
We're not. We will find a counterexample.
Okay.
Classical matter certainly does, though. So there is a counterexample known to you all, hopefully, and that is that if you think about what happens in the Casimir effect, that is, say, the self-energy of a quantum field between two perfectly conducting plates, you will discover that it's got negative energy density. This puts all theorems of this type and all theorems on stability of general relativity into a certain amount of confusion. It's not clear whether or not that is real confusion, but in order to make black holes evaporate, you need to have negative energy densities. And that also is a consequence of a quantum field theoretic effect. However, as far as classical physics is concerned, nobody knows of any counterexamples to positivity of energy. If there were some, it would certainly cause instability. And it's a very interesting question as what would happen.
Even from the classical point of view, here we're saying that we have, well, momentum's got to be positive. But we're trying to show that mass is positive, essentially, right?
We'll sort of succeed.
Isn't including that mass is positive because, I mean...
No, no, it's not circular, because the real problem is the gravitational energy. So when you're asking about whether or not the energy is unbounded, or is there a bound on the energy, the real problem comes from the classical potential energy. Remember that if you take a sphere of radius r and mass m, its energy, binding energy, will be the order of minus gm squared over r. That can be arbitrarily negative on the face of it, and it's that potential energy which is giving rise to a problem. Okay. That does not happen in general relativity. The questions that we are worried about are quantum mechanical effects, and where we're able to treat the quantum theory in a consistent way, we might be able to address the issue, but actually we can't. So, yes, it's worth worrying about, but not worth losing a whole lot of sleep about, because we can't do the entire theory. Where we're able to, the fact that we are here probably indicates that the theory is somehow stable. You could argue, well, that argument could go on for a bit. So I want to show that these three here, these things actually vanish before discussing any more of the details of what's going on. So you just write them out. So the first term is plus epsilon dagger h a b gamma c. Now what we're supposed to do is, of course, to take the covariant derivative of this unit time-like vector. So you will end up with a term that looks like KAC, the second fundamental form, and then you get a term involving the acceleration, which is TA omega c. multiplied by gamma E TE del, what is it? Must be B, right? Yes. The first thing to notice is the term involving acceleration goes away automatically. There's an HAB-TA, they're orthogonal, so you get nothing from that term. So you don't get anything involving the acceleration. The next term is minus HCD del D of HAB. But the simple thing to do is, of course, to remember that HAB is GAB plus TATB. The covariant derivative of the form metric G is 0, so you can replace this by plus TATB. So that just comes from the definition of the second fundamental, the first fundamental form. Then the remaining bits are epsilon dagger, gamma C, gamma A, gamma C, gamma A, del B, epsilon. The next term is the same. There's a plus epsilon dagger HAB del A of HBC, which you can replace by TBTC. And then there's a del C epsilon. Now at this stage, life becomes relatively simple. Here, if you take this term and you do not differentiate this t, it will hit this h and give you nothing. So that tells you straight away the only thing that's going to come from this is when you differentiate that term. This one, you just have to multiply out. So you end up with a collection of terms that involve the second fundamental form and the accelerations. The first thing is just what it always was, HAB, gamma C, KAC, gamma E, TE, del B, epsilon. Next, multiply out all these things. We're missing a bracket here. Minus HCD. Del D of TA is going to give me a KDA plus omega D TA, all multiplied by TB. Then we get a plus TAKDB plus TA omega DT. What have we got left? TA. Too many A's. Can't be right, it must be a B. Multiplied by epsilon dagger, gamma C, gamma A, del B, epsilon. And lastly, from this term, epsilon dagger, HAB, TC doesn't get differentiated. You've got del A TB, which gives me KAB plus omega ATB. Del A epsilon. What have I done? The last A is a C. And here it would seem. I don't know why I keep doing that. Now,
some of the second expression, or epsilon dagger, gamma A, gamma A.
yes. Should be gamma C, gamma A. This term here is obviously equal to 0 because omega and t are both orthogonal to h, but omega is orthogonal to h here, so that gets rid of those terms, and you're left with 4 terms involving the second fundamental form. which had better cancel if we have done this right. One of them does not seem to be quite right to me. Oh, no, it's all right. No, I know what's happened. Yes, it is all right. Let's see. This term, I think there is nothing that you can do with. It is going to cancel this one, I think. The technique is, of course, to write them out carefully using the same collection of indices in the same order. So you will end up with epsilon dagger, gamma C, gamma E, del B epsilon, and that gets multiplied by an HAB KAC, but H contracted with a K doesn't do anything, so it's the same thing as KBC. And then there's a factor of TE. The next term, this one here, is the same story, minus HCD KDA, so you can replace that by HCA. KCA. And then there's a factor of TB. Doesn't the C get raised? CA. Doesn't matter too much. And we're left with an epsilon dagger with a minus sign, gamma C, gamma A, del B. Let's write all of these with the up. No, that's right. Now, if you've done that right, these should cancel. Doesn't look quite right to me. Then there's an HCD KDB, so that's the same thing as H, so that's KCBTA. That also has a minus sign, and it's epsilon dagger gamma C, gamma A, del B epsilon. And then the last term here, there's an HAB KAB, so it's just a K. TC del C epsilon. And that's it. Epsilon dagger.
Is index C.
You want this one down. That looks better. Now, this one cancels this one. And this one cancels this one, although that's less obvious. This thing is symmetric under the interchange of C and A, so you can replace this by the symmetrized part of it, which is just the metric. Then GAC is HAC minus TATC. But TAKCA is 0, so that gives you nothing. That's the second trace of the second fundamental form. So it's that, and then that thing cancels that thing. So you get 0. So these three terms here just don't matter. They all cancel out. The net result is that the mass is equal to 1 over 16 pi integral of HAB del A epsilon dagger del B epsilon plus, get my factors of 2 right, cannot find it. Plus 8 pi times T D T D F epsilon dagger gamma F gamma C epsilon T C. So that tells you that the total mass has got a bit due to the energy momentum tensor, which is what you would expect, plus a bit which is inherently gravitational in origin. The bit that's gravitational in origin is greater than or equal to 0. The bit due to the energy momentum tensor of matter is also greater than or equal to 0, provided you make assumptions about the positivity of energy classically. So that tells you that the total mass must always be positive, and therefore your Newtonian fears about the stability of general relativity are unfounded. Is it possible for the mass to be equal to 0? Well, if this thing is positive definite, because energy momentum is positive definite, it implies that the energy momentum tensor must be equal to 0. Which I'll specify rather loosely like that. And it also means that del A epsilon must be equal to 0. This is an amazingly stringent condition. We've already seen that if del A epsilon is equal to 0, it implies that RABCD gamma CD epsilon must be equal to 0, which is a strong condition on the curvature. And if the curvature vanishes, you can find solutions of this equation. What is less obvious, and I will not attempt to prove, is that if you are asymptotically flat, the only solutions of this equation occur for flat space. In other words, Minkowski space. So if you demand solutions of the vacuum Einstein equations, then you've got to end up with Minkowski space. So, do that. That is essentially what we have proved. We have proved that the mass is bounded by 0. M is greater than or equal to 0 and vanishes if and only if space-time is Minkowski space. I cannot remember how many people are going to the supersymmetry course. All right, for those going to the supersymmetry course, you could say that the existence of supergravity means that this result is completely trivial. So, in any supersymmetric theory, if you are not doing supersymmetry, don't pay any attention to me for a bit. Well, in any supersymmetric theory you care to think of, there will be a set of conserved charges some of which, well, all of which are Q, the supercharge, which comes with a Dirac index alpha, the momentum, and the angular momentum. But one thing you do know is that if you take the anticommutator of two Q's, you will end up with gamma A alpha beta PA, where P is the momentum. Q, so these represent things which you could define at infinity if you had some nice supergravity type theory. But this is what you would end up with for any supersymmetric system, come what may. You know that Q is a Hermitian operator. So take the expectation value of this, then you'll discover that P0 is greater than 0. Which is, of course, what we've just proved. P0 is, of course, the mass. What is wrong with that proof? Well, actually, this is the same proof as this one. But if you actually wanted to carry out the proof, you'd have to construct a supergravity theory. And if you did construct a supergravity theory, you'd end up proving this inequality when you ask what is the expectation value of P0. So in actual fact, the motivation for this type of proof comes directly from supersymmetry. Now you can listen to me again. There is another proof of the positive energy theorem due to Schoen and Yau, which does not involve spinors. The result is identical. You will be appalled to discover it is much more complicated than this one. On occasions, Professor Gibbons has been known to try to teach this in the differential geometry course. I don't know whether he did this year or not. Nobody knows. The reason that I want to emphasize the spinorial way of doing it is its connection with supergravity theories and their connection with string theory. The arguments based on the existence of these spinors turn out to be amazingly powerful and can be used for all kinds of other interesting things. We don't really have time to discuss the generalizations of it, unfortunately. There are many generalizations of this argument, and they are, well, new uses still keep being found, even though the thing is about 20 years old. What I wanted to move on to now is what is usually called the second law of black hole mechanics. The second law of black hole mechanics is quite subtle. Roughly speaking, it's a classical theorem that again involves the idea of positivity of the energy momentum tensor. But what it says is, suppose you have some equilibrium situation with a black hole. That is stationary to start with. And you add some matter to it. That has positive energy momentum tensor in the same sense that we've already used it. Then the area of the event horizon must increase. The similarity of that result to the second law of thermodynamics is obvious, I hope. But I want to emphasize this is a classical theorem in general relativity, and it has nothing to do with statistical mechanics. For that reason, it is useful to see exactly how it works. Now, the easiest way to prove this theorem requires us to go back to thinking about how light propagates in a general space-time. Now, in case this is not familiar, the place to start doing this is from Maxwell's equations. Since I'm only going to be considering the propagation of light and not the generation of electromagnetic waves, these will be vacuum Maxwell's equations. So they're going to be del A of FAB is equal to 0, and that FAB is equal to del AAB minus del BAA. From these two things, I would like to have one further step. And remember that there are gauge transformations on A. That is to say, A goes to A prime, which is equal to the old one, plus the gradient of anything you like, gives rise to the same fields. Now that, of course, you can take and turn into a wave equation for A. And the easiest thing to do is just take the divergence of this equation. That gives you the wave equation. So del A of FAB is equal to del A of del AAB minus del BAA. So that's equal to box of AB minus del A del BAA. it is often a good idea to pick your favorite gauge, and I am going to pick the gauge del A equals 0. I'm going to pick this one because it is a covariant gauge and makes life easy. This thing, of course, should be equal to 0. This term is almost vanishing and would be if I commuted these two derivatives. So if you commute the derivatives, you will get that del A of AB minus R A B A C minus del B del A equals 0. So in my chosen gauge, that will disappear, and this turns into the Ricci tensor. So the wave equation is box A minus the Ricci tensor AC equals 0. If you were going to guess what the wave equation is, the chances are you'd forget this term. It's not what you'd expect. Or at least it wasn't what I expected when I first saw it. Now, how do you solve the wave equation in general and derive useful things about the propagation of light? The easiest way to solve it is in what is usually called the iconal approximation, in which you assume that the wavelength of light is very short compared to the scale of any curvature. That seems pretty reasonable for anything we're going to be interested in, because curvature tends to be small on the scale of the wavelength of light. Remember, the wavelength of light is of the order of a few thousand angstroms, or around 10 to the minus 7 meters. So the technique is to write in this approximation the vector potential A as A vector, which is real, times e to the I theta, and I'm going to put in an explicit factor of h bar to make theta dimensionless. So this you can regard as being sort of like a polarization vector, and this tells you about the oscillatory parts. So this tells you about the phase. This is like a polarization vector. So what is theta going to be? Well, the simple interpretation is to say that theta is equal to PAXA, and that defines, in a general sense, the form momentum of the light ray that you're considering. Were you to be doing this calculation in flat space, you can see that this is exactly correct. In flat space, little a, the polarization vector does not depend on where you are. And in a plane wave basis, you would say, oh, well, so A would look like e to the I pb xb over h bar. And to see that really is momentum, contemplate the momentum operator. The momentum operator is minus I h bar dA. So if that acts on A, let's call that C, otherwise we'll end up in a mess. PC with an operator, so we'll give it a hat, acting on AA is going to give me a minus IH bar. P doesn't depend on position. This thing is going to produce a factor of delta BC, and I get an I over H bar. Times AA. So that thing really is PC acting on AA. So that's why I chose to parameterize it that way. This defines generalization of the full momentum to a general curved space-time. If we stay in flat space for a moment, you can now see what the consequences of the wave equation are. First of all, the wave equation then implies that p squared equals 0. That's because in space the Ricci tensor vanishes and the box just gives you a p. And the gauge condition tells you that the polarization vector is orthogonal to the momentum vector. As you'd have expected in general. So this kind of way of doing things ought to be sort of moderately familiar, but we want to adapt this to curved space-time. What happens if you do that? Well, of course, there's nothing stopping me still writing the phase as e to the I theta over h bar, describing the oscillatory part of the wave. And I can still define a polarization vector out there, but what happens is that you will discover that this has to be replaced by a power series in h bar. That is not too surprising, because we said we're going to have to do something different to what we do in curved space-time. And remember that h bar we assumed is going to be small on the scale of the curvature. So what you need to do is take this as being the modified A and expand in powers of h bar. That is essentially the approximation that one has guessed that is supposed to work when the wavelength is short compared to the curvature. What happens? Let's first of all look at the gauge condition. That's del A equals 0. You substitute in that form for the magnetic potential, and you will get two types of term of AA plus h bar del A of BA plus h bar squared del A of CA plus dot 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 e to the I theta over h bar. Then there'll be terms coming from differentiating the e to the I theta over h bar. A plus h bar squared ca plus dot 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 e to the I theta over h bar, I over h bar, del A of theta. And now you can expand out in powers of h. There is a term, a single term that involves a 1 over h bar. That has got coefficient a del A of theta and nothing else. So that is the analogue of saying that the polarization vector is orthogonal to the gradient of theta. So in general, you could just simply say that you might like to call del A theta the momentum, in which case you'd say that PA AA was equal to 0 is a generalization of that. What then happens when you go to order 1 in h bar? So that's our initial approximation. Well, this, of course, is going to determine B for you. If you go to order 1 in h bar, you have a del A AA, and then from here you're going to have a B term contracted with P. So you'll end up with del A AA plus I PA BA equals 0. So that is a constraint on the form of B. In this gauge. Now we have to look at the Maxwell equations. Maxwell equations are a little bit more complicated because you have to take the second derivative terms. But there's nothing in principle difficult about this. You just have to calculate box of A minus R A B equals 0. So you just substitute in the same way as you did here and get a collection of answers. I'm not sure that I can do this in 2 minutes, but I'll try. There are terms involving box of each of these things. So you'll end up with box of A plus box H bar box of B, plus lots of stuff. Then there will be terms involving the second derivative of theta. That will give me I over H bar del B of theta, again into A plus H bar B plus dot 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 dot. Then there will be terms involving the gradient of theta squared. That will give me a minus 1 over H bar squared grad theta squared, again into AA plus H bar B plus dot dot dot. Then there will be cross terms in which you take the derivative of that once and the derivative of these once, which gives me a plus 2I over H bar del B of theta into del B of AA plus H bar del B of BA plus dot 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 dot. And lastly, there'll be some Ricci tensor terms that looks like minus RAB into AA plus A, BA plus dot dot dot, and the whole thing is multiplied by e to the I theta over h bar, and is equal to 0. So there you get a whole collection of stuff, and our next task is, of course, to try and carry out the same kind of expansion as before. Professor Green does not appear to be lurking outside, so we can do the next step. So, to order 1 over h bar squared, there is only one 1 over h bar squared term. It comes from here, there, and there. Since del A of theta is what we call the momentum, the only such term that there is minus 1 over h bar squared grad theta squared times A, and since little a is not equal to 0, it tells you that grad theta squared is equal to 0, or if you prefer it, that PA is equal to 0. So you discover that the light rays are still going to be null. Tangent to the trajectory of the light rays is null. We have to stop there because there is now a queue outside. So we will finish this off on Wednesday.